classifying real numbers. So jumping right into the gist of the lesson. So we see a set is a collection of objects called elements. So the elements are written within brackets. So three types of sets. We got an empty set, so there's no elements, nothing in there. We have a finite set, so that's where we have a limited number of elements within the set. Then lastly, we have an infinite set. So like here, we can see this looks like odd numbers starting at 1, so it looks like odd natural numbers, and the dot 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 called an ellipse. That means that the pattern continues on forever. So the next numbers would be 7, 9, 11, 13, 15, so on and so forth. So three types of set: empty set, nothing in there, no elements in there; finite set, a limited number of elements within that set; and then an infinite set is an unlimited or an infinite number of elements within that set. On the outside, we have our brackets, or sometimes referred to as braces. So here, one thing we notice, the difference between natural numbers and whole numbers have that 0. Just like there's an O in whole, I always think of, okay, there's a 0 in whole numbers. Integers, they're just positive and negative whole numbers. So we still got 0, still got our whole numbers, but we also have the negative versions. Note, here it decreases and the pattern continues forever because we see the ellipse still going all the way towards negative infinity. So it goes all the way towards negative infinity. And then here, the ellipse signifies that the numbers go all the way towards positive infinity, just going on forever. Rational numbers versus irrational numbers. Really important, rational numbers can be written as a fraction, or we can also think about it as the decimal either repeats forever with like the 0.333, or the decimal terminates, like here 1/2 becomes 0.5. So rational numbers can be written as a fraction, the decimal can terminate, like here in 0.5, or it goes on forever, like 0.3 repeating. Irrational numbers, they never stop or repeat. So with pi, that's the most famous irrational number I can think of. We know it's 3.141, and it just keeps on going forever, and it does not, we can't write it as a fraction. The decimal does not terminate, and there's no repeating pattern that we see within pi. And then real numbers, rational numbers, and irrationals fall underneath that umbrella. Yep, so here's another way to represent that. So we can see the rational numbers and the irrational numbers make up the real numbers. Yeah, and just note how we can categorize different sets of numbers within each other as well. All right, so practicing a few. If we look here, let's just go ahead and start with something such as 0. Remember that 0 is a whole number because I remember the O in whole, and it goes with the 0. And then therefore it's also an integer, and it's also a rational number because it falls underneath that umbrella. So it's a whole number, so therefore it's an integer and a rational number, and obviously a real number. Okay, let's look at something like 12. So we can see that that is a counting number, also a whole number, an integer, and a rational number. If we look at something such as, let's say 2.2, what we see is the decimal does stop, it terminates, so therefore it would be a rational number. Since it has that decimal in this place, the tenths place, it's not going to be an integer, whole number, natural number, and it does not meet the criteria for an irrational number because we see the decimal stops right there. All right, root 10. So we see if you type in root 10 on your calculator, you'll see that the decimal keeps going. There's no pattern. And when I put it on my phone, vertically, it only goes a few digits, but then when I tilt it horizontally, it goes even more. And there's no repeating pattern. The decimal doesn't stop. We cannot write it as a fraction, so therefore it would have to be an irrational number. Okay, so this slide just has the answers to other ones on the screen. We're going to keep moving on. Sets for real world situations. So different sets help us describe different real world situations. So here, the amount of cash in my wallet. And if you want to take a moment to pause the video and think through them through yourself, I'd really encourage that. But I'm going to start going over them now. So if you haven't got a chance yet, just go ahead and pause. And then when you're ready, after you've made your attempt to guess the answers to these, you can go ahead and resume the video. So the amount of cash in my wallet, I don't carry cash in my wallet, so therefore I'm classifying this as whole because it can be 0 or it can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you know, obviously with 1s, 5s, 10s, 20s, 50s, $100 bills, but we're never going to have a decimal if we're just dealing with cash alone. So the amount of money in my bank account. So there I know I'm going to have cents in there, so there's going to be decimals, but they don't go on forever. So they always terminate, and so therefore I'm going to classify it as rational. So the number of points scored in a football game. So assuming that a game can end in a tie of 0-0, I'm going to say the whole numbers. If you thought of it like it could never end in a tie, you know, some team has to score, then I could see natural numbers being another answer. Circumference of a round table. So if you forget the equation for circumference, I did. I had to go look it up. You can search it. It's pi times the diameter, or twice the radius times pi. And what we can see is since we have that irrational number in there, pi, this is going to be classified best using irrational numbers. Okay. Intersections and unions of sets. So intersection is any element in both groups. So what I really notice here is I notice the n in intersection. It looks like the symbol for intersection. So intersection is any element in both groups. Union is any element in either group. So here I notice the U matches up with union symbols. That's really nice. So let's look at them both. So what is the intersection of A and B? So again, the N, so I know it's an intersection, so I'm looking for elements in both groups. So here we see 2, 3, 4, nope, but we can see 6 in both. And we can also see that 12 is in both. So therefore, we see that the intersection of A and B is going to be 6 and 12. And then notice we don't have an ellipse, we don't have a dot, 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 because it does not continue on forever. So therefore, if this would be classified as a finite set. And then here, what is the union at A and B? So remember, union is any element in either group. So therefore, the union would just be every single integer here listed out. For the sake of time, I won't write this out, but we can see that the union of A and B would be 2, 3, 4, 6, 8, 9, 10, and 12. All right, continuing on, closure. So giving a certain operation, the outcome is also in this set. So let's look at an example. So the set of whole numbers is closed under addition. So here, I'm going to go back to my pen. We have a whole number plus another whole number, and that gives us a whole number. Here we have a whole number plus another whole number. It gives us a whole number. So what we can see is that since the answer is always a whole number, the set is closed under addition because you're only going to get answers that are whole numbers. However, if there's a statement and there is one example that proves that statement is false, we call that a counterexample. So let's look at some more examples. So to determine whether each statement is true or false, give a counterexample for false statements. So the set of whole numbers is closed under subtraction. So if you want to take a moment here, think to yourself, go ahead and pause the video now and try to attempt these 3 on your own, but I'm going to continue going over them right now. All right, so the set of whole numbers is closed under subtraction. So let's just say I do 5 minus 7, that's going to give us -2. So 5 and 7 are both whole numbers, but when we look, remember whole numbers are 0 and then the positive numbers going forward, so like the natural numbers going forward, but negatives, that's not a whole number, that's an integer. So therefore this statement is false because one counterexample proves that this is false, a false statement. All right, here, the set of whole numbers is closed under multiplication. So if we think, okay, any two whole numbers we multiply, we're always going to get a whole number in all cases. So that is actually true. And then here, the set of whole numbers is closed under division. So if we think about something like 3 all divided by 4, we have 2 whole numbers being divided here. But when we actually divide them, 3 divided by 4 is going to be 0.75. 0.75, again, we have that decimal, non-zero digits to the right of the decimal point. So therefore what we see, I should just write in 0.75, but therefore what we see is that this is going to be false because we found one counterexample and there are numerous, infinitely many counterexamples here, but the set of whole numbers is closed under division. That is a false statement. All right, so again, today we looked at classifying real numbers, and then your practice set is here. So if you want to go ahead and try the practice set, go ahead and do that. I'm going to show the answers in just a moment, so pause if you want to try this out. All right, I'm going to show the answers now. So here are the answers. Feel free to pause on the screen to just check your answers. And then lastly, our homework for today was L1, so the starred problems, so every single problem that has a star on it. And then you're also going to go do these extra problems as well. Again, email me if you have any questions. Thank you so much. Have a great day.